How long does it take to get to the planets in our solar system? To get to the planets in our solar system, you will need fuel. And I'm not talking about a small amount of it. The fuel is vital to send your rocket into interplanetary space. But it is also needed for maneuvers, corrections, and changing of orbits. You see, planets are moving in space. And if you think we only need to just aim and shoot, I'm sorry to inform you that you're wrong. It's a lot more complicated than that. There are actually many ways to reach a target, in our case the planets, and they are all different from each other. But one thing is sure, all of them make use of an amazing combination of math and physics knowledge. Thankfully, we have a solid description of how the planets of the solar system move in space. Their motion happens in the potential of the sun, and the orbits are almost circular. Let's say in general, they are elliptical orbits. This is indeed what Kepler found some centuries ago. So once we understand that the aim and shoot method can't work, we need a different approach. We could decide, for example, to reach a planet by means of the Hohmann transfer. This kind of transfer is basically the simplest one and can always be performed if you want to reach your target in a reasonably small amount of time. It is accomplished by placing the craft into an elliptical orbit that is tangential to both the initial and target orbits in the same plane. The maneuver needs fuel. It uses two engine impulses. The first places it on the transfer orbit by raising the craft to the target orbit's altitude, and the second makes the craft match the target orbit. The Hohmann maneuver often uses the lowest possible amount of impulse to accomplish the transfer, but requires a relatively long travel time compared to higher impulse transfers. The Hohmann transfer, however, imposes definite launch dates. The actual travel time will be given by half the time it takes to travel the entire Hohmann orbit, which is a value easily calculated through Kepler's third law. As I said, the Hohmann transfer makes use of a small amount of fuel in order to perform the orbital transfer. But if we wanted, we could go faster. How? Well, the answer is pretty simple. We could carry more fuel to boost our spacecraft. But this has some negatives. First of all, we would have to carry around a lot of extra fuel, which would also mean increasing the speed at launch. Basically, a dog biting its own tail. The second type of transfer that has gained a lot of fame and success during the last decades is the one that makes use of the so-called invariant manifold theory. Basically, you need to picture the space surrounding the planets as filled with many highways, and every highway is characterized by some value of energy. Basically, an object with specific energy will always travel on its own highway. That is the highway that matches its own energy value. This, of course, an uncomplicated and naive idea, but it gives you a taste of the mathematics and physics beyond this simple explanation. Such highways are always there, and they are stationary, invariant. That's why they are called invariant manifolds. The manifolds are mathematical objects, and they are created by the presence of the planet's potential. Now, the interesting thing is that such highways connect, for example, the Moon and the Earth, or Jupiter and the Sun, as well as the Earth and the Sun. And once you manage to put your spacecraft on a specific highway, characterized by specific energy given by the velocity of your spacecraft, you can basically go to the Moon and back, or to the Sun and back, with basically no fuel. You would only need it at the departure to get into the highway, and at some specific points of your trajectory, for example, when you decided to come back. Basically, what is put on the highway stays on the highway. But computations of such highways and the conditions to get on the invariant manifolds have to be really accurate, because these manifolds can be unstable, meaning that tiny deviations in energy or velocity can take you on a different highway very quickly. However, this approach is, most of the time, slower than the Hohmann approach, because the manifold orbits might have weird trajectories to follow, meaning that the highway could basically be a mess. Here's, for example, what the invariant manifold tube looks like in the case of the Earth-Moon system. Anyway, we also need to consider that the trip duration depends on the kind of encounter we want to have with the planet. There is indeed a lot of difference between arrival with orbital insertion and arrival with a fast flyover. For example, for a fast flyover, the departure speed can be preserved until the end without slowing down, meaning that we can spare some fuel. Also, you need to take into account that trips to the inner planets are really complicated, because in that case you are going toward, for example, Mercury and Venus, but you are also going closer to the Sun, and being attracted by its strong gravity is not an advantage at all. It's fine if you're content to only do fast flyovers, but if you want to orbit a planet like Mercury or Venus, you have only two options: braking with retro rockets to counteract the Sun's gravity, or losing speed by doing flybys with neighboring planets. Well, these are the basic principles of interplanetary navigation. Now, let's see how, during the years, space missions were designed and how long they took to reach the planets in our solar system. Let's start with Mercury. Distance from the Sun: 36 million miles, 58 million kilometers. Minimum distance from Earth: 56.5 million miles, or 91 million kilometers. Mercury is perhaps the most complicated planet to reach, despite being really close to Earth. To reach this planet, we have to follow a Hohmann orbit. This orbit would be huge: 192.6 million miles, or 310 million kilometers long. However, given the correct amount of fuel, we could cover this distance in something like 100 days for a nice flyover of the planet. Our spacecraft would be traveling at something like 37 miles per second, which means more than 124,000 miles per hour. We wouldn't be able to see much of Mercury. That's why, in 1974, when Mariner 10 made the flyover, becoming the first probe to get that close to Mercury, engineers slowed its speed so that it would have more time for photographic shots. The trip lasted 133 days. Mariner 10 is not the only probe we sent to Mercury. Bepi Colombo, for instance, was launched in 2018 and will reach the planet in 2025. The aim of this mission is to orbit Mercury to study this amazing planet. But in order to do so, the probe has to be slowed down. This can be done by making the probe lose speed by first encountering other planets. In fact, Bepi Colombo will fly by Earth, Venus, and Mercury. Performing gravitational slingshot maneuvers on such occasions will reduce fuel consumption, making it lower overall than that required for a direct route from Earth to Mercury, which might be faster, but of course also more expensive. As concerns Venus, its distance from the Sun is 79.5 million miles, 128 million kilometers, and the minimum distance from the Earth is 25 million miles, or 41 million kilometers. Despite its great proximity to Earth, the Hohmann orbit for Venus also involves a very long route of a whopping 249 million miles, 402 million kilometers, a distance that on average a probe could travel in less than 150 days. Venera 1, launched in 1961, was a Soviet probe that reached Venus in 97 days. However, it performed a flyby at a speed too high and then got lost in orbit around the Sun. See, This is what happens when you get closer to the Sun. But we didn't give up. The following year, NASA's Mariner 2 probe flew over the planet, but more cautiously, taking 115 days. The mission was a success. More recently, in 2006, ESA's Venus Express reached Venus using the main engine to reduce speed so it could be caught in a Venusian gravity. After launch and separation from the last of the 4 launcher stages, Venus Express spent 153 days in an interplanetary transfer orbit. During the cruise to Venus, the spacecraft was contacted daily for health checks and navigation using the high-gain antenna. The spacecraft was put on an arrival trajectory to Venus with mid-course navigation, and a final course adjustment was performed on 29 March 2006 to fine-tune the arrival hyperbola for Venus orbit insertion. Venus Express studied the planet's complex dynamics and chemistry and the interactions between the atmosphere and the surface, which provided clues about the surface's characteristics. It also studied the interactions between the atmosphere and the interplanetary environment, the solar wind, to better understand the evolution of the planet, and it observed the Venusian atmosphere and clouds in unprecedented detail and accuracy. Let's go to Mars. The distance from the Sun is 141 million miles, 228 million kilometers, and the minimum distance from Earth is 34.7 million miles, or 56 million kilometers. Reaching Mars with no rush would require a journey lasting about 8 months, which is necessary to cover the Hammond orbital path. However, the first missions were way faster than this because they were only programmed to fly over the planet and quickly take some pictures. They were Mariner 6 and 7, and this is one of the pictures they took. The slower and heavier missions, such as the 1976 Viking missions, took twice as long, about 300 days to enter orbit around the planet. Today, instead, if we want to land on Mars and make in situ science, we can reach the planet in 203 days, as the Perseverance mission, now on the sands of Mars, did. Now it is time for Jupiter. Distance from the Sun, 483 million miles. Minimum distance from Earth, 385 million miles. It took 640 days of flight for Pioneer 10 to reach Jupiter. Pioneer left in March 1972 and arrived in December 1973. It flew over the planet, keeping the same orbital path of the Hammond transfer orbit without ever slowing down. Later, in the late 1970s, the Voyager 1 and 2 probes also made a close pass of the planet, taking as little as 550 days of travel. The first really beautiful pictures that we have of Jupiter, however, came from the Galileo probe. It was the first probe to attempt to enter orbit, and it took 2,242 days to do so. In fact, after leaving in 1989, it had to make 2 gravitational flyovers of Earth and 1 of Venus to pick up considerable initial velocity and then decelerate enough to succeed in entering a stationary orbit around Jupiter in 1995, after more than 6 years of travel. Galileo also visited Jupiter's moon. Here's a beautiful picture of Europa, clearly covered with ice. The other gas giant, Saturn, is found something like 793.5 million kilometers away from Earth. Pioneer 11 was the second space mission after Pioneer 10 to reach Jupiter and the first to fly over Saturn. Only 4 spacecraft have ever made it out to Saturn. They are Pioneer 10 and 11, Voyager 1 and 2, and Cassini-Huygens. Our most comprehensive look at the planet came from NASA and the European Space Agency's Cassini mission, which spent 13 years exploring Saturn and its moons. NASA's Pioneer 10 mission launched on March 2, 1972, followed by Pioneer 11 on April 5, 1973. Though the missions launched about a year apart and had different trajectories, together they accomplished a number of historical feats. Pioneer 10 provided unprecedented insight into the asteroid belt and performed the first flyby of Jupiter, while Pioneer 11 was the first spacecraft to perform a flyby of Saturn. NASA no longer has contact with either spacecraft, but both probes have continued to voyage deeper into space. Both Pioneer 10 and 11 are on trajectories that will eventually take them out of the solar system entirely, each carrying a map back to Earth should any intelligent life ever intercept them. Talking about the Voyager missions, Voyager 2 was actually launched first in August 1977, but Voyager 1 was sent on a faster trajectory when it launched about 2 weeks later. They are the only two functioning spacecraft currently in interstellar space beyond the environment controlled by the Sun. Voyager 2's path took it past Jupiter in 1979, Saturn in 1981, Uranus in 1985, and Neptune in 1989. It is the only spacecraft to have visited Uranus or Neptune and has provided much of the information that we use to characterize them now. Because of its higher speed and more direct trajectory, Voyager 1 overtook Voyager 2 just a few months after they launched. It visited Jupiter in 1979 and Saturn in 1980. It overtook Pioneer 10, the only other spacecraft in interstellar space thus far, in 1998, and is now the most distant artificial object from Earth. Finally, Cassini made it to Saturn. It was launched in 1997 and reached Saturn in 2004. Then it orbited the planet until 2017. At the end of its mission, Cassini executed a maneuver called the Grand Finale. It circled closer and closer to Saturn's cloud tops between the planet and the rings. Then, on September 15, 2017, it plunged into the planet's atmosphere. This was the only way to ensure that it would never smash into any of Saturn's moons and contaminate them with any Earth microbes that managed to cling onto it. It continued transmitting data for 30 seconds longer than expected, but eventually it burned up. This is an amazing image of Saturn taken by the Cassini mission. We're running out of planets. Let's talk about Uranus. Distance from the Sun, 1,783 million miles. Minimum distance from the Earth, 1,690 million miles. So far, only one mission has reached the seventh planet in the solar system, Voyager 2, which took only 8.5 years to get to fly over the gas giant. It should be noted that the expected time to make the Earth-Uranus path following the Hohmann orbit is 16 years. With gravitational assists from Jupiter and Saturn, Voyager 2 was able to almost halve it. Finally, there's Neptune. With a distance from Earth of about 2,702 million miles, it is the furthest planet we have ever visited. Only one probe visited Neptune, the legendary Voyager 2, which after its encounter with Uranus flew over Neptune in 1989, taking 12.5 years to make the entire journey starting from Earth. If no gravitational assist had been performed, the journey would have taken them more than 30 years instead. You think we're done, don't you? Well, I would like to talk about Pluto too, because even if it is not considered a planet anymore, we care about it. Its distance from the Earth is about 2,672 million miles, and we have sent a mission to study it in more detail. The mission is called New Horizons. Launched in January 2006 with a speed of 36,372 miles per hour, it was the fastest man-made object to leave Earth so far. The spacecraft flew by the solar system's largest planet, Jupiter, for a gravity assist maneuver on February 28, 2007. The encounter increased the spacecraft's velocity by about 9,000 miles per hour or 14,000 kilometers per hour, shortening its trip to Pluto by 3 years. In this way, New Horizons was able to get to the dwarf planet in just 9.5 years. This, taken by New Horizons, is perhaps the most breathtaking picture of Pluto you will ever see. So on that incredible note, thank you for watching our video on how long it takes to get to the different planets of our solar system. I'm sure you'll agree that even though space exploration takes a long time, it's definitely worth it. Let us know what you think in the comments. If you had the opportunity to go to the outer planets, would you be willing to spend years traveling to get there?